Hello and welcome to week 6 of our differential equations course. This week we're going to cover these 4 sections: repeated roots of the characteristic equation, reduction of order, non-homogeneous equations, and then the method of undetermined coefficients. I'm going to start with a little bit of revision from last week's lesson. Last week we were looking at how to solve homogeneous linear second order differential equations with constant coefficients. In other words, we were looking at equations such as a y double prime plus by prime plus cy is equal to 0. And we saw that we need to find 2 linearly independent solutions of this differential equation, y1 and y2. After we know our 2 solutions, we can write down the general solution to the differential equation as some constant c1 multiplied by y1 plus some constant c2 multiplied by y2. The way that we were finding our 2 linearly independent solutions was, first we were looking at the characteristic equation, ar squared plus br plus c is equal to 0. Same numbers a, b, and c is in the differential equation, but we replace y double prime by r squared, y prime by r, and y by 1. We need to find the roots, let's say r1 and r2 of this quadratic equation. And we know there's 3 possibilities for the roots of the characteristic equation. If we have 2 different real numbers, then we saw that the 2 solutions that we want are e to the power r1t and e to the power r2t. If instead the roots of the characteristic equation are complex conjugates, then we saw that our 2 functions are e to the power lambda t cos mu t and e to the power lambda t sin mu t. The third case, the case when we have repeated roots, we didn't study last week. So let's do this now. Section 3.4 is about what happens if we have repeated roots of the characteristic equation. Consider our differential equation. But now let's suppose that b squared minus 4ac is equal to 0. Then we only have 1 root of the characteristic equation. Using the formula for the root of a quadratic equation, minus b plus or minus b squared minus 4ac over 2a. If b squared minus 4ac is equal to 0, then we just have 1 root minus b over 2a. So we know one solution. We know e to the power of rt, or e to the power minus bt over 2a, is a solution of the differential equation. But we need 2 linearly independent solutions. So we need to ask, how do we find our second solution? For example, and there's a mistake here, this should say solve y double prime plus 4y prime plus 4y is equal to 0. First thing to do is to write down the characteristic equation. The characteristic equation is r squared plus 4r plus 4 is equal to 0. And because this equation has easy numbers, it's easy to factorize this r plus 2 squared. So we can see that we have repeated root minus 2. So straight away we can say one solution is e to the power minus 2t. We need to find a second solution, a linearly independent second solution. And the idea goes like this. We know that y1 is a solution. So cy1 is a solution for any constant c. But what happens if instead of some constant c, we put a function in? Instead of looking at cy1, maybe vy1 is a solution for some special function v. If we can find the special function v, we multiply by y1 and our second. So we're going to consider y2, v of t, y1 of t, for some function v of t which we don't. We want to find this function. So let's start with y2 is v multiplied by e to the power minus 2t, y1. Differentiate this and then differentiate this again. And then I want to put these formula into the differential equation. Our differential equation, the equation we want to be true, is y2 double prime plus 4y2 plus 4y is equal to 0. If we substitute in, and I've just seen there's a mistake here, of course there should be a v just here, and rearrange, you will see that we end up with v double prime e to the power minus 2t. This is because e to the power minus 2t solves the differential equation, so most of the terms cancel out. So we have our special function v double prime must satisfy v double prime e to the power minus 2t is equal to 0. But e to the power minus 2t graph looks like this. This is always not equal to 0. It's always strictly positive. But because this part of the function is not 0, we must have that v double prime is not 0, is equal to 0. We can choose any function v which satisfies the rule that v double prime is equal to 0. There's infinitely many functions you can choose here, but because I like easy functions, I'm going to choose the easiest function which satisfies this equation. I'm going to choose vt is equal to t. And then we have y2 is equal to t multiplied by y1, or y2 is t e to the power minus 2t. But so we have these two solutions, and if we haven't made any mistakes, two should solve the differential equation. But are y1 and y2 linearly independent? To answer this, we calculate the Wronskian. And you can check that the Wronskian of y1 and y2 is e to the power minus 4t, which is not equal to 0. Because the Wronskian is not equal to 0, these two functions are linearly independent. We have these two functions. They're both solutions of the differential equation, and they're linearly independent. Therefore, we can say that they form a fundamental set of solutions, and we can write down a general solution. Some constant c1, y1, plus some constant c2, y2, or c1 e to the power minus t plus c2 t e to the minus 2. That was one equation. We could do the same thing for the general equation. Suppose we want to find general solution of ay double prime plus by prime plus cy is equal to 0. We know one solution, we talked about this earlier. One solution is e to the power minus bt over 2a. So we make a guess. We guess that the second solution is some unknown function of Vt multiplied by e to the minus Vt over 2a. And then we do what we did before, we differentiate and we substitute into the equation. And I'm going to skip the calculation here. I'm going to leave this for you to check. You can check that if y2 is equal to v e to the minus bt over 2a, and if we put this into a y2 double prime plus b y2 prime plus c y2, we get a e to the minus bt over 2a b double prime. So again, we must always have v double prime equal to 0. We can choose any function v which satisfies this. So we choose the easiest one. We always have v t is equal to t. So our second solution is then t e to the rt, or t e to the minus bt 2a. I'm going to leave it for you to check that the Wronskian of these two functions is not equal to 0. Therefore, e to the rt and t e to the rt form a fundamental set of solutions to the differential equation, and then we can write down the general solution. Let's do some examples. First, solve the initial value problem y double prime minus y prime plus 1/4 y is equal to 0, where the initial conditions y of 0 is equal to 2, y prime of 0 is equal to 1/3. You will see later why I've colored the second condition as red. We start with the characteristic equation, r squared minus r plus 1/4 is equal to 0. And from this, we see that we must have repeated root r is equal to half. As soon as we know our repeated root, we can write down the general solution. Our two functions are e to the power of half t and t multiplied by e to the power of half. So the general solution must be c1 e to the t over 2 plus c2 t. Next, we look at the initial conditions. And I'll skip through this quickly. I'll leave this for you to check. You can check that to satisfy the initial conditions, we must have that C1 is 2 and C2 is minus 2 over 3. And then we can write down the answer. The solution to the initial value problem is 2e to the t over 2 minus 2/3 t e to the t over 2. Another one. This is the same differential equation. The first condition is the same, but now we have a different second initial condition. I'm going to leave this for you to solve. Use the same method as in the previous example. Work it out on paper. You will see that the solution to this initial value problem is 2e to the t over 2 plus te to the t over 2. I'm going to show you the graph of this solution and the graph of the solution from the previous example. Here they are. The red curve is the solution to the initial value problem where y prime is 0 is inferred. This turquoise curve is the solution to the initial value problem where y prime is 0 is equal to 2. Notice that these two functions both satisfy the differential condition. They both satisfy y of 0 is equal to 2. In other words, both pass through this point. And the slope at this point is similar, but not exactly. Slope is equal to 1/3, or the slope is equal to 2, which is not a big difference. The difference between 1/3 and 2 is not a big difference. And yet, the behavior of these two solutions is very different. The red graph curves down to minus infinity. The turquoise graph curves up to infinity. just from this small change in the initial condition. Let's do a summary. To solve a second-order linear differential equation with constant coefficients, we need to find two linearly independent solutions. If the two roots of the characteristic equation are real numbers and different numbers, this is the easiest case, e to the r1t and e to the r2t. If we have complex conjugates, our two functions are e to the lambda t cos mu t and e to the lambda t sin mu t. And case 3, which we've just done, if we have a repeated real root, then the two solutions are e to the r1t and t multiplied by e to the r1t. This is the rule that we need to solve equation this. The second topic for today is reduction order. And this is a similar idea to the method we used in the previous section, but a little bit more sophisticated. Now let's suppose we are considering this linear second-order differential equation. Y double prime plus some function p of t y prime plus some function q of t y is equal to 0. Now the coefficients can be functions. And suppose that we know one solution to this differential equation. Suppose we know that y1 solves this differential equation, and suppose that we want to find a second linearly independent solution. We can use the same idea as in the previous section. We can make a guess that the second solution is some function v of t multiplied by y1. Anytime we do reduction of order, anytime you have reduction of order question, the way we start is we always start with y2 is equal to v multiplied by y1. For some unknown function vt. The idea is we want to try to vt. If we know vt, then we know y2. Question in the text is there a book I need to get? You don't have to buy a book for this course. If you look in OLearn's content section, you'll find my lecture notes. That might be enough for you. If you think you want extra information, I've suggested 2 good books there, which you could choose from if you wish. But this is up to you. If you want to buy a book, get one of these. If you don't want to get a book, that's fine. Some students will find my lecture notes are enough. Some students will decide that they also want to get a book. You must decide. Okay, so let's do some reduction of order. We know that y1 solves the differential equation, and we're going to make the guess that y2 is equal to v multiplied by y1. We differentiate using the product rule, v prime y1 plus v y1 prime, and then differentiate again using the product rule to get y2 double prime is v double prime y1 plus 2v prime y1 prime plus v y1 double prime. And I'm going to take these 3 equations, these 3 formulae, and I'm going to put them into the differential equation which we want to be true. We want y2 to satisfy the equation y2 double prime plus py2 prime plus qy2 is equal to 0. So we're going to substitute these 3 formulae in. There we go. And then we're going to rearrange. We get v double y1 plus v prime 2y1 prime plus py1 plus v multiplied by this term. And look at this term closely. Y1 double prime plus py1 prime plus qy1. We know that y1 solves the differential equation. We started by saying, if we know that y1 solves the differential equation, how can we find a second solution? So because we know that y1 solves the differential equation, this final bracket must be equal to 0. When you do reduction of order, you must always get an equal to 0 at the end here. Always 0v. If you get something other than 0, then it means you've made a mistake in your calculation. You need to go back and find your mistake. We must always get equal to 0 here. So this is 0. We can cross this out. We have 0 is equal to v double prime y1 plus v prime 2y1 prime py1. Let me repeat what I just said. Because y1 solves the differential equation, we must always get plus 0v on the end. It's okay to have something multiplied by v prime. Okay to get something multiplied by v double prime, but we must always get 0v. If you don't get 0v, then you've made a mistake. Now, this equation is actually a first-order differential equation. This may seem unusual because we have v double prime, but just to understand this, we can make a substitution. We can replace v prime by u. Then instead of v double prime, and instead of v, we have u. This is a first-order differential equation for u. We know how to solve first-order differential equations, so we can find u. And then after we find u, we can integrate to find v. And then after v, we can do v multiplied by y1, and this will give us our second solution, y2. So this means instead of having to solve a second-order differential equation to find the function y2, instead we only need to solve a first-order differential equation to find this function u. Hence the name of this method, reduction of order. We are reducing a second-order problem to a first-order problem. Let me repeat the method. Anytime you do reduction of order, this is what we're going to be doing. We know that y1 is a solution, and we make a guess that y2 is equal to v multiplied by. We put this into our differential equation, and we find an equation for v. Then we make our substitution. We let u be equal to v prime. We have a first-order differential equation. We solve the first-order differential equation to find u. After we know u, we can integrate to find v. And then finally, as soon as we know v, we do v multiplied by y1, and we have our y2. If I give you a reduction of order question in homework or on the exam, I'm going to phrase it like this. Given that y1 equal to 1 over t is the solution of this differential equation, find a linearly independent second solution. We're going to use the method from the previous slide. We are told that y1 is a solution. We're going to guess that y2 is equal to v multiplied by y1. Here's y1. y1 is 1 over t. We're going to start with the guess y2 is equal to v multiplied by y1. So we start with y2 is equal to v multiplied by t to the power minus 1. Differentiate 2 times, and then we substitute this into the differential equation that we want to be true. We want y2 to satisfy this differential equation, so we want 2t squared y2 double prime plus 3t y2 prime by 2 to be equal to 0. Here we go, substitute these in, rearrange. Before we go on, let's look at the final bracket. Remember I said the final bracket must always be equal to 0. What do we have? 4 minus 3 minus 1. 4 minus 3 minus 1 is equal to 0. So this is all 0. And what do we have here? Minus 4 plus 3 is minus 1. We have 2t v double prime minus v prime. Let me repeat this. We need to find a function v which satisfies 2v double prime minus v prime is equal to 0. We make our substitution to turn this into a first order equation. We're going to substitute u to v prime. We need to solve the first order differential equation 2t du dt minus u is equal to 0. This equation is linear and this equation is separable. So you know 2 ways to solve this equation. I'm going to solve this equation as a separable differential equation. This is the whole calculation. When you read the lecture notes or when you watch the videos, you can check that this is correct. Please check that there's no printing mistakes here or that I haven't made any mistakes. Please check that we end up with u is equal to some constant c, t to the power of a half. For the time being, let's leave the constant c just here. So we have u is equal to c multiplied t to the power of a half. And to find v, we're going to integrate this function. The integral of this function is 2 over 3 c t to the power of 2 plus some new constant k. And then y2 is going to be v multiplied by y1 or v multiplied by t to the power of minus 1. And we get 2/3 ct to the power of a half plus kt to the power of minus 1. We can simplify this by choosing or making a smart choice of the constant c and k. The first thing to note is we're trying to find a solution which is linearly independent from t to the power of minus 1. The second part of our solution, k t to the power of minus 1, this is not linearly independent from y1. This is just constant multiplied by y1. We don't need this. We don't need the k t to the power of minus 1. So we can choose k is equal to that's okay. So that makes it a little bit easier. 2/3 ct to the power of half. And this should work for any non-zero small c. We can't choose small c is equal to 0 because then we'll just get y2 is equal to 0. And that's not really independent from c1. But any number c other than 0 would be okay. And I like easy numbers. I like easy functions. So just to make this nice and easy, I'm going to choose c is equal to 3 over 2. Then we have the nice easy function t to the power half. I'm going to leave it for you to check that the Wronskian of t to the power minus 1 and t to the power of a half is not always 0. In other words, I'm going to leave it for you to check that these two functions form a fundamental set of solutions. And that's the answer to this problem. Let's do another one. Given that t solves t squared y double prime plus 2ty prime minus 2y is equal to 0, find a second linearly independent solution y2. Reduction of order questions, we always start the same way. We always start with the guess that y2 is equal to v multiplied y1, which in this example means y2 is equal to v multiplied t. Differentiate 2 times, and then substitute into the differential equation. I'm not going to go through this step by step in the class. Please check that this is correct. You know that sometimes I make mistakes on these slides, so please check that there's no mistakes just there, and this is actually correct. You will note that, as always, we have 0 v terms. We only have v double prime and we have v prime terms. So we can do the usual substitution, u is equal to v prime. T is going to be a positive number, so we don't need the t squared. We can forget about the t squared. Substitute u is equal to v prime, and we have the first order equation, t du dt plus 4u is 0. We can solve this as a separable differential equation. Again, I'll leave this for check. I think we get c t to the power minus 4. Leave the small c in for the time being. We'll choose it later. Right, what do we have? We have y1 is equal to t, v prime is equal to u, and u is equal to ct to the power minus 4. We can integrate u to get minus 1/3 ct to the power minus 1/3 plus k. And then write down y2 minus 1/3 ct to the power minus 2 plus kt. We don't need the plus kt because that's just a multiple of y1, so we'll choose k is equal to 0. Then we have minus 1/3 c. Again, I don't want this. We'll choose the correct value of c to get rid of this. And the function that we want will be t to the power minus 2. So what we're going to do is we're going to choose c is minus 3, and we're going to choose k is 0. And we'll get the solution that we want. y2 is t to the power minus 2. If I haven't made any mistakes, then that would be the end of the answer. But if you have free time in an exam, or if we're doing the homework and you want to double check your solution, it's worth answering 2 questions. First question is, does this function really solve the differential equation? Did we make a mistake, or do we really have a solution? We can differentiate and we can put in, and we find that we're equal to 0. So the answer is yes. This function really does solve the differential equation. The second question that we should ask ourselves is, are these two functions linearly independent? To answer this, we calculate the Wronskian. And we calculate the Wronskian is not equal to 0 because t is always a positive number. Therefore, y1 and y2 are linearly independent. This means that we didn't make a mistake in that calculation. That means our answer is correct. y2 equal to t to the minus 2 is the correct answer to this question. Moving on, section 3.6 is about non-homogeneous equations. Now I want to consider y double prime plus pty prime plus qty, and now instead of being equal to 0, I want this to be equal to some function gt. Homogeneous means equal to 0 here. Non-homogeneous means equal to some function just here. Anytime we have a non-homogeneous equation, we can also consider a similar equation, but instead of having equal to g, we could have equal to 0. This is called the homogeneous equation corresponding to equation 5. We have a theorem which tells us what solutions of equation 5 look like. The general solution to equation 5 can be written like this. c1y1 plus c2y2 plus some function capital Y, where y1 and y2 form a fundamental set of solutions to the homogeneous equation corresponding to 5. In other words, the first part, c1y1 plus y2, we already know how to do this. We've been studying this earlier today and last week. c1 and y2 are constants, and capital Y is a particular solution to equation 5. In other words, it's just any solution to equation 5. So what we do is we solve the homogeneous equation corresponding to 5. We find one solution, any solution, a particular solution to equation 5, and then we add them together. For a particular solution, we need a new way of writing it. I prefer to use capital Y, it's easy for me to remember. You will find some books you look in, they use small y subscript p for a particular solution. That's just different notation for the same thing. I would say when you write your answer to an exam question, make sure your small y and your capital Y in your handwriting are distinct. Don't write them quickly and make it so that these two letters look the same. So to solve the non-homogeneous equation, L of y is equal to g. This is the same as the differential equation, equation 5. We have 3 steps. First, we find the general solution to the homogeneous equation, L of y is equal to 0. We need to find one solution to the non-homogeneous equation. We call this a particular solution, just any solution. And then we take our 2 functions and we add them together. In this course, we're going to study 2 different methods to do the second step. One method we're going to study this week, and the second method we will study next week. The first method to do step 2 is called the method of undetermined coefficients. And the idea goes like this. The first thing we do is we look at our function g. And we're going to make a guess. We're going to guess that our particular solution looks something like g. But we're going to make a guess which includes some constants. And then we try to find the constants. If this works, if we can find the constants, then we have our particular solution. I'm going to do some examples. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 3e to the 2t. We're going to look at this function. We're looking at the function g. We have some number, in this case 3, multiplied by an exponential function, e to the power 2t. So we're going to guess. We're looking at this function and we're guessing that our solution looks like this. We're guessing that our solution is also some constant multiplied by e to the power 2. And then we're going to try to find this constant capital A. If we can find capital A, then we have our particular solution. So we calculate capital Y is a e to the 2t, and we differentiate 2 times, and then we substitute into the different equation. We start with y double prime minus 3y prime minus 4y is equal to 3e to the 2t, and we substitute for capital Y and simplify, and we get that minus 6a e to the 2t is equal to 3e to the 2t. We need to use the constant capital A such that these two things are the same. So, of course, we choose A is minus a half. Then we have the answer to this problem. A particular solution is minus a half e to the power 2t. Let me repeat the idea. We're looking at this green function. The green function is some number multiplied by e to the 2t. And we guess that the solution is also a number multiplied by e to the 2t. We try to find capital A. If we succeed, then we have the answer. Another one. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 4e squared minus 1. We're going to look at the green function and we're going to make a guess. Green function is a second degree polynomial. So we're going to guess that the particular solution is also a second degree polynomial. A t squared plus pt plus c for some numbers a, b, and c. I leave this example for you to finish. In fact, this is going to be on your homework to finish this example. You will note there's a word here which might be a new word for some of you. This word Ansatz, which was from the German language, means a mathematical guess. So instead of saying we try to guess capital Y is equal to at squared plus bt plus c, we can write we try the ansatz capital Y is equal to at plus bt plus c. Next one, find a particular solution to y double prime minus 3y prime minus 4y is equal to 2c. Here's our function, 2 sine t, number multiplied by sine t. We look at this function and we make a guess. I'm going to guess that the particular solution is also a number multiplied by sine t. You will notice that I've written first guess here. This should be a hint for you straight away that I'm not going to be the final guess in this. We differentiate 2 times and we substitute into the differential equation. And we find that 2 sine t must be the same as minus 5a sine t minus 3a cos t. On the left side, we have sine 2t, and effectively that's also plus 0 cos t. So on the right-hand side, minus 5a must be the same as 2. And minus 3a must be the same as 0. So for this to work, we must be able to solve the linear system minus 5a is equal to 2, minus 3a is equal to 0. This linear system does not have a solution. This linear system is inconsistent. It's not possible to find a constant capital A which satisfies both of these equations. So this guess was a failure. So we guess again. This guess was a failure because if we start with sine and we differentiate, we also get cos into the function. What else can we start with that when we differentiate it with sine and cos terms? We could start with our second guess, a sine t plus b cos t. Differentiate 2 times and substitute into the equation. I'll leave this for you to check later. We must have 2 sine t and then effectively plus 0 cos t is the same as minus 5a plus 3b sine t plus minus 3 minus 5 cos t. So a and b must satisfy the linear system. Minus 5a plus 3b is equal to 2. And minus 3a minus 5b is equal to 0. This linear system is consistent and we can find a solution. I'm just going to tell you that this linear system is minus 3 over 17. I think there's a typo here, isn't there? Well, check this later. I think there's a typo here. I don't think we should have 7 and 7. Check this and see if you can find the correct numbers. We don't want to dwell on this. 17 it should be. There should be a 17. So a particular solution is minus 5 over 17 sine t plus 3 over 17 cos t. Before I go on to the next example, let me just remark about this. We should consider that sine and cos are friends. They always go together. If you see either sine or cos in your GT, then your ansatz needs to contain both sine and cos. Likewise, shine and cosh, my friends, they should always go together. If g of t contains one of these, then your guess at a particular solution should contain the other one. Next example. Find a particular solution to y double prime minus 3y prime plus 4y is equal to minus 8 e to the power t cos 2t. We look at our function on the right-hand side. Minus 8 is a number. Then we have an exponential function, e to the power t, and then we have cos 2t. So we guess that we should also have some number, in this case, let's say capital A, exponential function e to the power t, cos 2t. But then we remember, whenever we have cos, we must also have sine as well. So we remember that we must also have another number, capital B, e to the power t, sine 2t. Then we differentiate this function 2 times. I shall leave this calculation for you to check. Substitute into the differential equation, and then look to see what do we have. We have minus 10a minus 2b on the right and minus 8 on the left. Multiply by minus 1 just to get rid of minus signs. We must have that 10a plus 2b is equal to 8. We also have 2a minus 10b et sine 2t on the right, and on the left we don't have any terms involving sine, so this must be equal to 0. Solve this linear system using your techniques from linear algebra to find a is 10 over 13 and b is 2 over 13. As soon as we know a and b, we can write down the answer. A particular solution to this differential equation is 10 over 13 e to the t cos 2t plus 2 over 13 e to the t sine 2t. Theorem. Let's suppose we have something like this equation, which I'm underlining in red, where on the right-hand side we have two functions, g1 and g2. What we can do is we can cut this up into two easier problems. The equation is equal to g1 and the equation equals to g2. If we can find a particular solution y1 which satisfies this equation, and if we can find a particular solution y2 to the second equation, we can add them together to find a particular solution to a different equation on the. For example, a particular solution to y double prime minus 3y prime minus 4 is equal to 3 2 sine t minus 8 e to the t cos 2t. On this right-hand side, we have three functions. And what we're going to do is we're going to cut this into three smaller, easier equations. So just imagine we cut here and we cut here. Instead of this long, complicated formula, we're going to look at three easier problems, which I've colored green, orange, and blue. But we've already done these three. We already know particular solutions to these three differential equations. Using the previous theorem, therefore, we can just add them together. a particular solution to equation 7 is given by this long function. We have this green function, which is a particular solution to the green differential equation, and then plus the orange function, which is a particular solution to the orange differential equation, and then plus this blue function, which we've just seen as a particular solution to this blue differential equation. So to recap, find a particular solution to our non-homogeneous equation. We've been looking at our function gt, and we've been choosing a similar function capital Y. This doesn't always work. There's one difficulty that occurs, as I'm going to show in the next example. Find a particular solution to y double prime plus 4y equals to 3 cos 2t. Our first guess, and again there's a hint to you that this is not the last guess, we use the idea from before. We have 3 cos 2t, that's a number multiplied by cos 2t. So we guess that we also want a number multiplied by cos 2t, and every time we have cos, we must also have sine. So we must also have a number multiplied by sine 2t. Differentiate and put into the equation, we get 3 cos 2t is equal to 0. And this must be true for all t. But no, that's not right. This is a failure. Not possible to choose the constants a and b such that 3 cos 2t is equal to 0 for all t. This guess did not work. Why did this happen? Why didn't our usual method to solve equation work? To understand why this didn't work, I want to solve the homogeneous equation y double prime plus 4y is equal to 0. Quick, this should be revision for you. We start with the characteristic equation. Here, r squared plus 4 is equal to 0, which tells us that the roots must be plus or minus 2i. So the general solution to the homogeneous equation must be constant c cos 2t plus constant c2 sine 2t. And because cos 2t and sine 2t are appearing in the general solution to the homogeneous equation, we can't use the same functions for a particular solution. If we try to use the same functions as the previous page, we just get the equation is equal to 0. We need some different function which, when we differentiate them, give us cos 2t and sine 2t. And the rule, if in doubt, if you need new functions, the rule is we should multiply by t. Remember what we did when we were solving repeated roots of the characteristic equation? We took our first solution and we multiplied by t. We're going to use the same idea here. We need two functions which, when we differentiate them, give us cos 2t and sine 2t and perhaps some extra. We're going to use t cos 2t and t sine 2t because when we differentiate these functions, we get cos 2t plus something and sine 2t plus something. So, second guess. Now I'm going to guess that capital Y is AT cos 2t plus BT sine 2t. That's the First guess multiplied by t. We use our same method. We differentiate 2 times. We substitute into the differential equation, and we get 3 cos 2t is equal to 4b cos 2t minus 4a sine 2t. This we can solve. Straight away, you can see minus 4a must be equal to 0, and 4b must be equal to 3. So we must have that a is 0 and b is 3/4. Then we're finished. Then we have our particular solution, 3/4t sine 2t. Please remember that you can't use the same functions in the general solution of the homogeneous equation and in the solution. If you think you need to use the same type of functions, multiply the function in your particular solution by t. If it doesn't work, multiply by t again and keep trying. And that is the end of today's lesson. Next week, we're going to finish chapter 3. We'll look at solving initial value problems. We will look at our second method to do step 2. Instead of the method of undetermined coefficients, there's another method called the method of variation of parameters. And then we will finish by looking at higher order linear ordinary differential equations. Do you have any questions? Question, when is the midterm exam? The midterm exam is going to be in the 9th week of term. Yeah, 3rd of December, and I think it's 12:30. So it's half an hour earlier than we normally have a lesson. The Dean's office will be announcing the exam schedule sometime this week if they haven't already done so. You can find all of your exams there. Yes, it's going to be online. I'll send more information via email nearer the time. It's going to be the type of exam where you receive the questions. You need to write your solutions on paper, showing all of your method, all of the steps you use. Take a photograph of your paper and then upload the photograph into OLAN. Which parts are we responsible for? Everything we cover before the exam. So everything that we cover from week 1 to week 8. Okay, so if there are no more questions, you're welcome to leave whenever you wish. I will be here for another 10 minutes. How will the exams be? You will receive questions, and you must solve the question by writing your answer on a piece of paper. Take a photograph of your piece of paper and then upload the photograph into OLearn. What would the questions be like? They will be similar to the questions in the lecture notes, similar quality to the problems in the lecture notes. Will there be a face camera? This will be announced closer to the exam. It depends on if the system can cope with that many students uploading video at the same time. Not just 1 to 3, there will also be the start of chapter 4. We will start talking about the Laplace transform before the exam, and I can ask questions on the beginning of chapter 4 as well. Then the time announced by the Dean's office is the correct time. Yes, I've just looked at the syllabus. You are correct. I wrote the syllabus a long time ago, before the exam schedule was finished. I should correct that.